Hello, hello. We're getting started now. Thanks for your patience while we handle some last minute end of semester things happening. Hope you're all getting your projects in. Your projects in. So you're working on your project updates, your project drafts. So, but today we're gonna have some fun. We're gonna finish off this operational space controller that we've been talking about for a couple of weeks now. And really it started, with us building the simulation. Actually, let's just remind ourselves of the glory of what we have going on here. We have this inverse dynamics controller that we've had. Anyway, so we had this double pendulum, this robot arm under gravity, okay, that we derived the dynamics ourselves. Look, we're watching it derive the dynamics right now. We ran this code. This code is online. You can grab this code on the files page on Canvas. Oh, look, there's a robot arm. Okay, it's doing things that might be hard to recognize. Let's turn off the controller. Let's turn off the controller. Where's our controller in our code to see where we were at? Where's our controller? Boom, 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 boom. Here, tau, no controller. Let's uncomment that. Get rid of our other controller. So you can see what happens when we have no controller on this double pendulum. This double pendulum that we derive the equations of motion ourselves by setting it up in MATLAB, and it does all the symbolic toolbox fun stuff, right? So that's all good. And let's see. But then we can turn on this inverse dynamics controller, okay? And this inverse dynamics controller allows us to set the acceleration, this desired acceleration here, ddq desired, the second derivative of our positions, which is our accelerations of our joints, okay? And let's say, hey, I want those accelerations to be 0. Well, guess what? This inverse dynamics controller will come up with the exact torques it needs to make the acceleration 0. And sure enough, you're watching the animation of this right now. Those joints are not accelerating, okay? All right, there's a torque there and a torque there. And it's holding in the exact right torque. And it doesn't matter what happens to the position we want to hold. Let's say let's change our starting position to pi over 2 and pi over 2. This is going to make a little upward elbow, okay? Look at that. Oh, look, upward elbow. Ugh. Strong arm, right? Holding it in place. All the torques are being calculated so it holds it in place. And even if we make the masses bigger, so let's say we made the second mass, instead of being 0.5, we made the second mass 5, something much bigger, right? The inverse dynamics controller says, okay, that's fine. I know I have to adjust my torques accordingly in order to hold it in place. That's it. Isn't that neat? Now, awesome, right? We did all that from scratch in MATLAB. I think that's pretty cool. So, but let's take it a step further, because there are a couple of things in the inverse dynamics controller, which, if you just sort of recall here, here's our notes from last time, my friends. So we have this double pendulum, and the idea of the inverse dynamics controller is that we take our desired accelerations, which are in our what we call the joint space, meaning that we have this joint, we have this joint, right? We're commanding accelerations of those joints, right? However, what we might care about is the task space, not the joint space. So let's go here back to that. So inverse dynamics, this is just a continuation of the notes from last time. Inverse dynamics commands accelerations of the generalized coordinates. Those are our degrees of freedom. In this case, we have the shoulder and we have the elbow, okay? Those 2 degrees of freedom, those generalized coordinates. And that's the second derivative of q. So q double dot with respect to time, right? All right. That's what it does, okay? And it gives us the torques out. That's what we're seeing, right? But what we've been talking about is the idea of having a task space. So what if we have a task space or an operational space is a function of your coordinates, your Q's, your positions. That represent a useful target. The idea is you have some Q of T. Those are the positions of your joints. That's what we call sometimes joint space, all right? Sometimes we'll call that, joint space, right? Then we have some mapping, just some function. You put into some function, and out comes, let's say, some task, okay? Let's call it Z of T. It's some task, okay? Task, those are your joints. Okay, I got a whiny dog. Whiny dog wants to join the lecture. Yeah. Whiny dog join the lecture. Little guy. All right, hang out right here with me. All right? Hang out. Right. So, joining the lecture, having fun. All right. So, moving on, we have this task space. So, we take our joints and we get our task out. Now you say, well, so there's some function here. We'll call it F just for the moment because it is a function. All right. But the idea is that we would say that Z of T, your task, is equal to some function of Q of T. And for a robot arm, it is this end effector a lot of the time. It's the thing you care about. Who decides the thing you care about? Ultimately, at the end of the day, you do. The person setting up the task, you care. But a very common one for a robot arm is the end effector, the very end of the arm. So the example would be the end effector. All right. So, for instance, when we have our double pendulum, which I'm so good at drawing right now, right? Whoop, whoop. You got your theta 1, then you have your theta 2. Theta 1, theta 2. That's your end effector. End effector. Effects the world. Okay? All right, and you got your two lengths. You got L1, you got L2. It's all under gravity, of course, etc. And there's a mass 1 and a mass 2. Well, you could say that your task space, this end effector, okay? Let's say that Z of T is just going to be the vertical and horizontal coordinate, the Cartesian coordinate right there, X and Y, of the end effector. So let's write that as a vector. Your X coordinate is going to be, L1 cos is L1 sine of theta, because again, the angle is oriented down like that. Sine of theta 1 plus L2 sine of theta 1 plus theta 2. Hopefully, it's implied that the trigonometry, all of those are grouped together inside of the trig function. And then minus L2 cosine of theta 1 minus L2 cosine of theta 2. Well, it's theta 1 plus theta 2. Because this angle theta 2 is relative to the first angle theta 1. Okay? That's right. And then there you go. That is your task space. That's simple, right? That's just what we define, right? And it could be more complicated. You could have the task space be, for instance, the center of mass of your robotic arm, right? You could say, hey, what's the position of this mass? What's that mass? And you want to say, hey, I want to control where the center of mass of that arm is. Okay? And that's something that you could do. And you could just change your task space so it's now the center of mass of your robotic arm. You could literally just write out the math for it, right? Okay, so that's what we're going to try to do today. Is we're going to use operational space control. Do one thing is to control it in task space. So in operational space control, the idea is that you want to control task space coordinates. Okay, but also we can add limitations on things like torque. Okay, for instance, we can have so we don't have infinite torque on this arm necessarily. Okay, right now we're saying we can apply whatever torque we want, but in reality we have torque limits, and there are limits on maybe a particular arm configuration can only accelerate so fast. It's possible that you might not be able to get the exact task-based motion that you want. So let's try to get as close as we can. And getting as close as we can, doing the best that you can, there's a name for that process. It's called optimization, a big part of this class, right? So we can deal with limitations. So we can have limits and constraints on the physical system. Okay, that's what we're going to do. So we have limits and fits. So that's where, and the way we'll achieve that is via an optimization. And we talked about this before. We could actually turn it into a quadratic program, a QP. QP is nice. QP solves fast, P, especially if it's convex. And guess what? This one will be convex, my friends. And the way that we set this up is we say, hey, we want to have our optimal decision vector W, the optimal being the star, is equal to the argmin, the minimization. We want the argument, the input that minimizes. What's the best decision? That gives us the difference between our Z double dot desired, Z being our task space, right? It's our task space acceleration, what we want, minus what we actually got, which is Z double dot of T. Or I guess in this particular time, at this particular moment in time, we're at some moment in time T. And we're going to do a 2 norm, meaning that we're going to square all the elements, take the square root, then we're going to square it. So it's just the square of all the elements. Okay, very much. So this is minimizing that. So this is trying to get as close as you can between what you want and what you got. It's going to try to drive this difference to 0, right? That's your cost function. Okay, subject to the constraints. And we talked about this before. We actually include as our constraints the physics of our system, our dynamics. Okay, where m of q times q double dot, the actual acceleration you're going to achieve, is equal to some function of q dot, and tau, which is everything that is not an acceleration term, and therefore an inertial term, everything else, right? That's how we've been writing our dynamics for these Lagrangian mechanics systems, okay? That's how we've been writing that out, right? And also we can add limits, right? And specifically limits on our decision variables. We haven't even talked about what our decision variables are yet, but we have talked about in previous classes. Our decisions, of course, are going to be all of our torques. If we have multiple torques, there are multiple of them in that vector, okay? But also, we have our q double dots, okay? So if you have all your accelerations, your taus, and you have all of your q double dots, right? Okay, and why are those there? It's so that way you can set up this constraint to easily compute what your accelerations would be by setting up this equality constraint. And you could also, of course, have inequality constraints. You could say, hey, all of your taus are greater than or equal to tau min and less than or equal to some tau max, right? Those are torque limits. We call that saturation. So if you are limited on how much torque you can apply, as any physical system is, right? And it's not enough to do what you want, well, guess what? This optimization is going to do what? The best it can. All right? So what are we going to try to do? So again, look, I've been talking about the math. What are we physically going to try to get the system to do? We're going to try to get this arm to track to a desired point, right? And to do it in a way that is consistent, where if you change the dynamics of this robot, let's say right now we have, let's go to our thing. We said that the M2 weighs 5 kilograms. Say it makes 0.5, okay? Change the 0.5 kilograms to the second M2. That if we change the masses, if we change the lengths, if we change the inertias, the torque limits, whatever we want, it will still do its best to track some point for its end effector right there. Woo, okay, all right? That's the goal. That's the goal. And this optimization we will run this. This is a quadratic program. We will run that QP as a controller, meaning that for our feedback control loop, okay, we're going to have some Z desired, okay, where we want to go, right? And this is the task space, right? Okay, and then you're going to take in, that's a positive, that's a negative. So this is going to be our actual Z, our actual position, our actual task space. Oh, you can't see anything. I'm sorry. You can't see that. Did anyone stop me? Also, I can't see the chat. 1 second, friends. Okay, hopefully that didn't take too long. Let me make sure I see the chat. No one popped up and told me. That's okay. All right. So anyway, I just added this feedback control loop. Okay. Hopefully you saw the saturation. Hopefully you saw this whole deal right here. All right. And this feedback control loop. Okay. We're going to take in our desired task. Okay. This is where we want to be. Okay. This is where we are in task space, our end effector, the end of our robot arm, right? You're going to subtract them out, right? It gives us a difference. Okay. This is going to go into a controller. Give a little box that says controller. Okay. So basically what this is an error in our task that comes in. Then out of our controller, what we're going to want to have is our Z double dot desired, our acceleration. Okay. And that acceleration we're going to give to our QP, our optimizer, to come up with the best possible torque to send to our plant, which is our system. Okay, that's our torques. And then out of that comes Z. That's our feedback control loop. So this QP, this quadratic program, this optimization that we're running, its job is to give us the best torques and then tell us what the best accelerations it can achieve in the joint space, Qs, right? It'll tell us those, assuming we give it a Z double dot desired. Just remind us, there's Z double dot desired right there, okay? Who decides that? We do, okay? So while we have a desired position we want to get to, for sure, right? Maybe even desired speed of in our task space, we still have to decide how we take that error and turn it into Z double dot desired. Well, guess what? How we typically do it? We do it with a PD controller. Okay, we would say KP times our error plus KD times the time derivative of our error. Okay. We choose these gains, which tells us how fast we want to accelerate to our point that we want to get to, right? We choose that, right? But the beautiful thing is, once we choose those, if we in fact put in our QP the right dynamics of our system, we can change those dynamics. As long as we change the QP, we get the same behavior of the physical system. All right. Sorry, that's a lot there. But what we can do now is start to encode, put in our code, how setting up this quadratic program so that way we can solve it. Okay. And it's going to be inside this loop. So we're going to be simulating. And every simulation step, we're going to ask ourselves, hey, what's this PD controller? Hey, send that Z double dot desired into the QP. Hey, that gives us our torques, and that's what gives us our accelerations in our plant, which is our physical system, of course. So if we go back to our code, right now, in our code, our controller is right here. Again, this is up on the Canvas page. You can follow along. Get all our MATLAB code. So no worries, no issues there, but that's really simple. Look, that's just the inverse dynamics. It's M times Q double dot minus your F is equal to 0. That's the manipulator form of the dynamics. We just put that all in there. Okay? It's one line of code. That's the controller. This is going to be a little bit more complicated because we have to set up an optimization. So we're going to want to have our own standalone function file to be this controller. Okay? And what's it going to require? I'm glad you asked. Because this is Look, these are pretty advanced algorithms we're running together. These advanced control algorithms that we're all started from scratch in this class, just simulating systems, and we're marching forward to this. What a ride. What a fun ride, at least for me. So now we need to, so for our controller, what do we need? Okay, we need to have a QP solver. Okay, that's going to be quad prog within MATLAB, although there are many quadratic programming solvers in real life that are open source. You could use OSQP, which is an operator splitting QP solver. There's Gurobi. There's lots of options. Okay, you can just Google them. There are many, and they're good for different things. But they all solve quadratic programs. It's a question of how fast they are, more or less, or what kind of physical device will they fit on, right? So you have some QP solver. We'll use quad prog. Okay, what does quad prog need to solve? Well, as you recall from our prior work, let's go check. Let's see. Help quad prog. It needs an h, which is your Hessian of your cost function. That's like the second derivative of your cost function. The f, which is a gradient of your cost function. This is the a and b for your linear constraints, and your aeq and beq for your linear equality constraints. You can put upper bounds and lower bounds. You can give it an initial guess if you want. We typically don't in this class. We don't really, for our simulated systems, we can get away with that. If we wanted to solve faster, we can theoretically give it an initial guess that's closer. More on that, but where that's useful is if you need it to solve more quickly, especially so if this isn't a control loop as this is, right? If you want this control loop to run fast in real life, you might not want it to. Might want this QP to run as fast as possible. Give it an initial guess, right? We don't have to do that here. So moving on. So back to this. So what we're going to need for every step of this controller, we're going to need to generate H, F, A, B, AEQ, and BEQ. And those are going to be dependent on a number of things. What are they dependent on? They are dependent on, as you can see, oh, look, that matrix has a Q in it. It's dependent upon that. This vector here is dependent upon Q and Q dot. That's our position and velocity of each of our joints. Okay, this is a decision variable. That's okay. That is here, that's a decision variable, Q double dot. That's okay. Our cost function, is going to depend on Q and Q dot. Just as a reminder, this term here, this Z double dot, okay, while Z double dot desired is decided by this little controller, this PD controller here, that gives us out the Z double dot desired, right? That's easy enough. We compute that error, not a big deal, okay? Knowing what our actual acceleration is a big deal. Okay, so how do we get that? Again, we did derive this math a little earlier. So the idea is that, well, if z of t is some function, your task space function of q of t, right? If you want to take the time derivative of z of t, because what we want to get to is z double dot, right? You can write this using the chain rule instead of saying just f, that it's just f dot of t, q of t. You can actually break this down to say it's actually the partial derivative of f with respect to q times the partial derivative of q with respect to t via the chain rule. Okay? And this, my friends, we recognize on the left as being our Jacobian. That's a Jacobian of f with respect to q. Guess what? The MATLAB symbolic toolbox will happily do a Jacobian for us, right? Okay. And this term right here, that term is q dot, right? That's partial q, partial t. That's q dot, right? We know that. So therefore, it's equal to j q dot. And then if you want to come up with the acceleration in task space, that's z double dot. We take another derivative that's equal to the ddt, the time derivative of j q dot. Well, this is a product rule thing, right? This is just a product rule situation going on. So we would say that it's equal to the time derivative of j times q dot, so the derivative of the first times the second, plus the derivative of the second times the first. So jq double dot. Again, just knowing how to take a derivative, very handy skill, and it applies here, right? So if we compute our Jacobian and we compute our time derivative of our Jacobian, well, guess what? That's z double dot of t. Okay, we can get that by multiplying by q dot. That's going to be an input to our function. And q double dot, that's one of our decision variables. Done. Okay, so let's go into the code and try to set up these particular quantities into the symbolic toolbox. We're going to say, hey, what is our task space? We've already written that out. It is the end effector position. We use some trigonometry to figure that out. Not that hard, right? Then we're going to take the derivative of, we're going to take the Jacobian of that task space to get us j. You know, j specifically in this case is equal to partial f partial q, right? And then we're going to take the time derivative of j. We can do all that stuff, no problem, in the symbolic toolbox. And also we're going to see, can we get away with just ignoring this? We might be able to. We'll see. Okay, there's the time derivative of j is a term that you can often just get rid of, and it's more complicated than you need, but we'll see. We'll see. All right, back to the code. So now I'm gonna take this code I have right now, which is sim inverse dynamics, is the one that I have open right now. Again, you should have access to that in your Canvas drives. I'm going to save. All right, I'm gonna call it sim operational space. Okay, now it's a new function file, a new script file to run everything. This is now the 16th, the sim operational space, and simulation an operational space controller. Okay, now what do we need to define? Well, I'm glad you asked. We need to define our operational space. We'll call that z. Where do we define this? Let's define it. Here we have the vectors to our masses right here. Okay, so we're going to define our task space. Okay, I'm going to define it as z. Okay, and the good news is that z is equal to, where is our little fun thing? Here we go. We had actually previously defined these vectors, R1 and R2, in order to define the positions of our masses, M1 and M2, right? And you can see that we did this here for the purposes of computing our energies for Lagrangian mechanics. You might recall that, right? Where R2 is the position of our end effector. So guess what? Z is equal to R2. This is the position of our end effector. Okay? Not bad. Not bad. So this should all still run. Nothing really has changed. But I also want to compute the, so we're also going to need the positions of, so we're going to need our Jacobian, right? So let's take our Jacobian. We'll call it capital J. Our Jacobian. It's the Jacobian of our task Z with respect to what? It's the Jacobian with respect to Q. All right. So what I'm going to do is I'm going to run all this. I think unfortunately it's going to run everything, including the simulation. Okay. Yeah. So I have to wait for just a second. I want to see what comes out of J. Once we're done simulating here, when we're done, okay? I'm going to say, hey, what's in J? What does that look like? And sure enough, there we go. Look, that's J right there. Okay, neat. That's J. Still dependent upon time. At some point, we're going to have to get rid of that time dependence. Just like we had to do, is a trick we had to do back when we were doing the Lagrangian mechanics. That's just going to be a handy thing so that way we can make the functions that we need. We'll get to that in a second, though, right? So we have J. Three things that we needed. We got our Z. We've got that right there. Boom, we've got it. All right, what else do we got? Question. the question is do I have to get rid of the t and do those tricks? The way I've been doing it, I haven't found an easy way to get around having to get rid of the time dependence. If there's a way to get around it where you don't have to get rid of it, yes, you have to, when you're simulating something, you got to pass in a time anyway. That's true. Where I would run into problems is when I had to, I guess what you have to make sure you have to make sure you're passing in the right number of arguments to different functions. You might be able to get away without doing it. If you could, Marco, if you could think of a way to do that, that would just simplify a little bit of the code for us. But I think that'll be a lovely thing. But I do it for, I've been burned in the past, so that's why I get rid of it. Thank you very much for the question, Marco, in my ear. I appreciate that from the Zoom. Awesome, cool. We have J. All right, what else do we need? We need J dot, right? J dot right there. So that's just derivative of J with respect to time. That's what the dot means. So we're going to call it DJ. All right. It's going to be the derivative of J with respect to time. That should be fine too. All right. It should be able to calculate what that is. In fact, let's just zoom up and see if we can find it in our math here. All right. Where's DJ? Right. I missed it. Anyway, but it's at the bottom. Let's say DJ. There you go. Okay. I think the reason as well, we're gonna have to substitute in like this when you have the where's the this diff QDT. We have to make sure we do a substitution. That's the other thing. We gotta make sure we substitute in Q dot, and this is like not an expression. It's not like a variable. I think that might be one of the reasons, Marco, that we have to do that. But anyway, so we're gonna do the same. So we have Z, J, and DJ, right? The only trick we want to do is now get rid of the time dependence and substitute in, for instance, when we did our substitutions and say, hey, wherever we saw DDQ, we want to substitute in DDQ dot. We can do that. All right. How do we do that? Well, let's copy this code the way I set this up here. Copy, copy, copy. Okay, I'm gonna change this to Z and Z. Change all these things to Z. Okay, and wherever it would see a Q, it'll substitute in a DQ. All right, and also I want to at the very last second. Let's see. Put this behind this plug in the arbitrary time. This whole thing where we plug in the arbitrary time. So we're going to say, then we say Z underscore, which is the non-time dependent version of Z, just as a way to differentiate it from one from the other. It's just equal to Z 0. Okay. Let's just run that to make sure that that works. This should automatically substitute in wherever it saw Qs and DQs, and it actually puts in a variable called DQ, etc. Okay, so we check by saying, hey, what's Z underscore? And boom. Z underscore is a sign of theta 1 plus theta 2, theta 1 underscore. Don't have to worry about the time dependence. It's all figured out, okay? And let's do the same thing for J and DJ, the time derivative of J. So we're just going to copy this, okay? Do the same trick, okay? We're going to say, a little sloppy, we're going to say J, J, J. We're going to make this J, J, J. Here's the thing. Technically speaking, there will not be any time derivatives in J, but, you know, whatever. We don't have to do all three of those steps, but just an easy copy paste. And we'll do the same thing with DJ, the time derivative of J. Okay? So we're going to say DJ, 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 DJ. And then DJ, 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 and DJ, right? It's a little bit sloppy. It's not the cleanest thing I've ever done in my life, but that's as bad as it gets, okay? I mean, make sure you can see everything, right? And once this is all done running, we can check and say, hey, did all these things come out as non-time dependent versions of themselves where you can just substitute in the Qs, right? Let's see. So if we look at Z underscore, beautiful. Let's look at J underscore, non-time dependent version of that task space Jacobian, okay? Indeed, looks good. What about DJ underscore? Looks good. Okay, look at all those 9 time dependent versions. Look, there's D theta underscore, D theta 2 underscore, etc. Looks all good. So just to write this all out in the code, where do we write these things? This is the, we'll call this the task space Jacobian, right? And this is the time derivative of the task space Jacobian, right? So if we want to then compute based upon all this stuff, we can create, we already know what z underscore is. That's, we've already computed that. We can say that dz underscore, we can use this expression is equal to j times q dot. So time derivative of our task space, how fast we are moving the end effector. Literally, it's the speed in each direction of the end effector position. That's z dot. How do we compute that? It's equal to jq dot. jq dot right there. So j times q dot. So j underscore times dq underscore. That's q dot, right? And ddz, right, is equal to what, friends? It's dj underscore times q dot dq underscore plus j underscore times ddq underscore. These are the non-time dependent versions, right? So we run all that. This gives us our expression for our actual accelerations in the task space of the end effector there, okay, right? This is the task space acceleration. This is the task space velocity. Velocity. All right, and let's go up here, and this is our task space position for our operational space controller. Done. Okay, look at that, what we got here. All right, so moving forward. So we've got our task space acceleration written here, okay? We've got our task space position, our task space velocity. We've got, I think, everything we need to start setting up our quadratic program right here, okay? So this is an optimization problem. What three things do we need for our optimization problem, my friends? Let's set up our optimization problem. So we have our optimization. Three things. Number one, let's do our decision variables, our decision vector of multiple decision variables. Okay? Okay, that's W. It's going to include all of our torques and all of our accelerations. Okay? And transpose it so it's a column, right? Now our cost function, we'll call it J of W just because I've already used F, and I apologize for it. Our cost function. Again, it's going to be the difference between some from Z double dot desired minus Z double dot square. That's the 2 norm, and then we square it. Okay. Again, so the idea is then you have, oh, hey, Jeremy, are you okay? Hanging out? Good. Sorry, Jeremy. Didn't mean to kick you. All right. All right, buddy. So, you all good? You all good? With me. So that's our cost function. That's pretty simple. Then we have our constraints. We have equality and inequality constraints. Well, our equality constraints are going to be our M of Q double dot is equal to F of Q dot, and tau. Okay, and this will turn out to be a linear constraint, and we'll know this by pulling out the constants of this multiplied by all our decision variables. You will see that Jacobian and that is going to end up being full of constants with no decision variables in there. Okay, so we're going to have that. We're going to have our constraints, and we're going to have limits. So we're going to say tau is less than or equal to tau min and tau max. Okay, we'll add on these things as we go. You'll notice that we have not defined Z double dot here exactly, but it's that PD control law, okay? So Z double dot is going to end up being, Z double dot is going to be equal to some, is going to be equal to some KP, of Z desired minus Z plus KD z dot desired minus z dot. We have all those functions, okay? So what we can literally do in our code is we can write out our cost and our decision variable. We can literally write these out in the symbolic toolbox. So let's do that. So, all right, we've got here. Okay, let's, before we simulate, we're going to say, we're going to write our optimization variables and functions. Okay, here's our decision vector. Okay, our decision vector is two things, right? It is all of your torques first, then all of your accelerations second. You can play with the order however you want. It'll all work out as long as you're consistent in how you handle the math. So our decision vector W, okay, is going to be equal. It's going to have our tau vectors, right? I believe that's it. There's no underscore for tau. There's only one tau. There's no time dependence on tau, right? Yes. Tau 1, tau 2. Where do we define tau? There it is. Yes. Okay, good. It's not no time dependent, so don't have to worry about that. No underscore. And our accelerations, ddq underscore. Okay, that's our decision vector. Okay, for our QP, right? Now we're going to have our cost function. Okay, and that's going to be down here. Okay, what this is it's going to be the let's see, it's the 2 norm. We can write this a couple of ways. Given the fact that it is, I could write it as saying cost is equal to the norm of z double dot desired, ddz desired. Let's define that later, okay? Let's just say it's ddz desired currently, say equal to 0 to make our lives easy. We'll change this later, okay? All right, the norm, the 2 norm, that's what the vertical bars are, right? By default, minus ddz underscore, right? And then we square it. We can totally do that. We can, in fact, run all this, and we can check and see what the cost looks like, see if that makes sense, okay? See if the math works out all right. If it does, that's so cool, we won't touch it. Let's see, look, once it's done running our simulation of doing nothing. Okay, let's see, what's our cost function look like, my friend? All right, yeah, there's absolute values. I don't love that. Okay, yeah, there's absolute values in technically speaking. So there's a different way to write this 2 norm, keeping in mind that all we really want is that if you say, hey, if I want to take the norm of some vector v, right, and it's a 2 norm, that's just saying that it's equal to v, the vector norm v is equal to, if v is equal to v1 through vn, we're running out of time. Time is going fast. It's equal to the square root of the absolute value of v1 squared plus dot 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 plus vn squared. What we really want at the end, and then we're going to square it again. That's the 2 norm. Okay. What we're really looking for is just each of these elements multiplied by each other, right? And you can dot product it with itself. So the easy way to write this is that if we want the square of it, the square of our 2 norm, we could write this as v transpose times v. Okay, that'll be a dot product of v with itself. That's how we're going to write it. So instead of being the 2 norm in our code right here, we're going to call it, so we're going to say, hey, we have this vector, we're going to call ddz desired minus ddz, okay? Transpose, which is the dot apostrophe. Don't forget the dot, because then that way it's not the conjugate transpose. We don't want to change anything about the complex numbers. ddz underscore desired minus ddz. The same thing, right? We're dot producting, this is the inner product with itself, the dot product with itself, which will give us what we want, right? Done. That's our cost, okay? Now, if we run that, we check out that cost will be good. Then we're going to check out our constraints, okay? So now we're going to have 2 types of constraints. We're going to have, our, first, let's do our equality constraints, right? What's going to try to put it into the form to start with? We're going to say the form that we want some equality constraints, GEQ, of all your decision variables equals 0, okay? So if we set it up in that form, okay, where we have GEQ equals 0. I'll zoom in real close so you can see. All right, GEQ of W is equal to 0, right? Then what if this is in fact a linear constraint? This will get written as partial GEQ, partial W, times W is equal to some vector, okay, which is negative GEQ of 0. Basically, this, my friends, becomes the A matrix. This becomes the B vector, okay? So it's AW is equal to B. That's our equality constraint, our linear equality constraint, okay? So let's write everything in terms of GEQ equals 0. Let's get a little bigger now that we're here, okay? So what that's going to be is it's going to be, if we want to take the constraint that's M of Q, Q double dot, these are our dynamics, right? Is equal to F of Q, Q dot, and tau. We've computed already in our previous work M and F, okay? We got that from our Lagrangian mechanics, right? So we want to turn this into a function which equals 0. Very simple, right? M of Q times Q double dot. Subtract from both sides this term. So it's minus F of Q, Q dot, and tau is equal to what, friends? It's 0. So this left-hand side, that's GEQ, right? And it's dependent upon what, friends? It's dependent upon our decision vector W. What's in our decision vector? Our taus and our Q double dots, okay? And you'll find when we put all this math together, when we take the Jacobian of this, it should be filled with constants with respect to the decision vector. It should be no decision variables in that matrix. It should be a constant matrix A. And then everything left over will be B, okay? So let's get that. Let's actually write that out. So in our code, with our equality constraints, we're going to say that GEQ, is our only equality constraint here, is going to be equal to M. Is M dependent? Let me just double check on M. Is M dependent on? Good. I'll make sure that M is only dependent upon these 9 time dependent variables. It's going to be good. It's important because for all kinds of reasons. It's going to be equal to M times DDQ underscore, right? Let me just zoom in on this equation. Minus F. Is it minus F? Isn't it just F? F contains, yeah, perfect. F contains F1, but yeah, exactly. It contains everything, including our taus, right? Done. That's GEQ. I'm just running it to show that it still runs. We don't hit any errors, okay? Good, we don't. Awesome. So that is our equality constraints. So if we want to know what our A matrix is, our A matrix is just a Jacobian of GEQ with respect to our decision vector W. And B is equal to the minus, is the negative, because we're putting it on the other side, okay, is all the constants left over when you substitute in 0 into your equality constraints. We've done this before in much simpler contexts where we have zeros of the size of W to make sure that's the right size, okay? That's A, and this is AEQ for the equality constraints and BEQ for the equality constraints. When we run that, okay, what do we screw up here? W, did I not define W yet? Okay, it must be a 1 by n vector versus n by 1 vector. Oh, okay. W needs to be a column vector. I screwed up. That should be a column vector. So this W up here, that should be a semicolon. So that is a column vector. So if you run that, having changed that to a column vector, everything should be okay. Not quite. What do we do this time? GEQ zeros of size column vector. Okay. Oh, subs with an S. Subs with an S. It should be right there. That should run now. Nifty, cool, neato, awesome, neat. Okay, looks like it ran without issue. It's still running the simulation. When it's done, we'll just see what AEQ looks like. AEQ, what's it look like, friends? There it is. And it is filled with, and it has no decision variables in it. It's got theta, but it does have angles in it, right? Theta 2, theta 2, theta 2, theta 2. All right, what about BEQ? A little bit more complicated. Actually, there's something weird going on. Something with size is weird. What's the size of BEQ? Excuse me. Size of BEQ. 8 by 1. There's something off about that. What did I screw up? Zeros of size W. Something not right there. No, is that right? 1, 2, 3, 4. 8 by 1. This is a 4 by 2. There's something wrong with the size here. What am I screwing up? What's GEQ? What does GEQ look like? GEQ? What's the size of GEQ? It would just be 2 by 1. That's right. Okay. So that, let me just do some math here. There's something not quite right, I think. So given the fact, so the A matrix, okay, because there are 2 degrees of freedom for the system, you're going to have 2 constraints, that the acceleration of your first joint and your second joint, they're going to be 2 different constraints. So that's going to be A2 by what? Well, in this case, it's a 2 by the number of decision variables, n, and your decision vector, w. Then w is going to be an n by 1. Let's take a look at w. What's w equal? Okay, w should be 4. Okay, that's right, because we have 2 torques and 2 accelerations. That should be correct. However, this b, if we're doing the matrix multiplication here, this 2 by 1 times 2 by n times n by 1, the result should be a 2 by 1. These outer matrix dimensions, it's a 2 by 1. So what's going on in the code? Why is that not working? Let's find out. So I want to get this done because that way we can show the beauty of this controller as we okay. Minus subs zeros. Okay, maybe this line is wrong. Zeros of size W. That is 4. 1, 2, 3, 4. What's GEQ? Oh, I see. I didn't tell it what I'm substituting it in for. Where there were once W's, I want to substitute in zeros. Okay. I screwed up the substitution command. Okay. So where there were once W's, I want there to be zeros. Plug in zeros, please. Okay. That's going to make a difference. And the A, so the A matrix should be a 2 by n. What's the size of A? AQ, I should say. 2 by 4. 2 and n is 4. That's right. Right. Now let's look at this. Now let's look at B. Sorry, BEQ. Lowercase BEQ. It looks like it should be 4 by 1, right? Oh, 2 by 1. Yeah, that's right. It's so yeah, it's 2 by 1. Just like we said, like there. Okay. We can say, hey, what's the size of BEQ? 2 by 1. Boom. All right. We just had to say that where there were once W's, we want zeros. And that facilitates this expression right here. Minus GEQ equals 0. Okay. Just a little bit of a typo. All right. That's great. Hey, there's AEQ and BEQ. Those are equality constraints. We've already figured that out. Hey, for our cost function, we also had to get our Hessian, right? Let's look at our Hessian. We'll call it our Hessian, a capital H. Capital H. It's our Hessian of our cost function. We forgot to do that. That's what we need for the quadratic program. It's take the Hessian of the cost with respect to W. Run that. That'll give us H. Okay. And for everything else, we just need to know what's the gradient. Yes. Let's take a look at H. It should be constants with respect to the decision vector. And sure enough, it is. Here's H. It's going to be a 4 by 4. Some of these, it's going to be a square matrix 4 by 4. I see thetas, and that's good. I see thetas, but I don't see any accelerations or torques, which are decision variables. That's good. We got H. Okay. Nifty, neato, cool. Actually, might be able to all put this all in one line. This is going to be pretty crazy. All right. So we're moving forward. We got our Hessian. Okay. Now, keep in mind that's for quad prog. Just a reminder, quad prog, we then also need the gradient. Okay. And the way that we get the gradient, we can, of course, just take the gradient. They call it F. We're already using kind of F. I'm going to call we call it C, and I'm pretty sure I don't use C anywhere else as our gradient. Okay, that's going to be the gradient of our cost with respect to all our decision variables, right? But here's the other thing. What you'll recall that gradient is going to have all those quadratic terms in there. There's still going to be decision variables in there. So we need to substitute in zeros again where there were once decision variables. Because if you look at C, look, this is C right here. I'm seeing decision variables. dd theta, that's a decision variable. What else is here? Yes, so you'll see some decision variables in there. And we don't want those terms, okay? Those show up in the quadratic terms. This is the Hessian for the quadratic terms. Just like we did in class, some examples for the quadratic terms, okay? Here we want the linear terms from the gradient. So so we have to make sure we substitute in C. Wherever there was one C, we want to substitute in. Hey, when we had decision variables, we want them zeros. Let's zero them out. Zeros of the size of W. Okay? So that should make a new gradient, and this should only contain the linear terms. So let's take a look at C when it's time to pop up. Great. So I think that we're humming along. Okay? So this eliminates the quadratic terms. Right? Neat, nifty, cool. Cool. Yeah, C is at the right size. Yeah, it should be a 4 by 1, indeed, because there are 4 decision variables. All right, I'm looking at that. I don't see any decision variables. That is our C vector, okay, for our gradient, our linear terms for the cost function. Oh my goodness, we're close to done, friends. The only thing we haven't defined are our inequality constraints that say we have torque limits, okay? And we're going to put those, we can put those as inequality linear constraints. We can totally do that. Or we can just add bounds, okay? So we're going to add bounds in addition to this. So we have our constraints. We have equality constraints. We're going to do our inequality constraints. We're just going to say they're empty matrices for our linear inequality constraints. So A, which I don't believe we're using, we'll call it A ineq, is an open closed bracket. We'll say B ineq for inequality constraints is open closed bracket. We don't have any. Let's do our bounds. Okay, LB and UB. Okay, LB, our lower bounds on our torques are going to be minus tau min, which we need to define, then minus tau min for our 2 torques. And for our accelerations, we don't want to tell what any limits on accelerations. We theoretically can, but let's not do that. So minus infinity, meaning it can go as low as we want to go, right? And then we're going to do our upper bounds. It's the same thing. I'm just copying and pasting. Our upper bounds is just positive that, right? And you all in your own heads could have written a much more succinct way to define these than I did. I just did it like that, okay? Now, if I run this, this means that, what did I screw up? I didn't define tau min. Let's set a tau min. Let's make it big for right now. Let's make it 100 Newton meters. That's pretty big. I think it would be fine, right? All right. So right now, we should be able to define every element. What did I screw up? Oh, this is a comma instead of a semicolon. Big screwed that up. All right. That should work. Oh, I did the same thing. Semicolon. Right? Semicolons for all. This is why you don't do it the way I did it. Anyway. We got them. We got everything we need for the quadratic program. But you will note that our Hessians, all these terms, they are dependent upon our current pose. What's our current angle? Theta 1, theta 2. That's our Hessian, H, right? So that means 8 is going to have to become a function, right? We're going to have a function that takes in our current Q's and Q dots for all these terms, right? So watch this. Watch this. This is what we're going to do. Okay, so we're going to have to make more MATLAB functions that take in those terms. All right. So we use the MATLAB function called MATLAB function that takes some symbolic variable and turns it into a function like this. Okay. How are we doing this? Let's go into let's create MATLAB functions to compute our optimization terms. Okay, so for instance, we can create a MATLAB function called, we'll call it hfunc for our Hessian functions is equal to MATLAB function. What does it take in? Well, it takes in h, And as its variables, we're going to say, hey, what are the variables? It needs to know Q. I think it only needs to know Q underscore, right? Let's see. Just double check H. I'm pretty sure H only requires that. We could just include H. I think it only needs Q. Might need DQ. Just to be safe, we'll include DQ. I think fundamentally it only requires Q. But it could be wrong. So let's just do DQ underscore. So it takes in both. We want to do the same thing for our C function, for our linear terms, for our cost, right? C, Q, and DQ. They are not dependent upon torques. No, of course, they're decision variables. Of course, they shouldn't show up at all, right? Q and DQ. Nice. We also want an AEQ function, which is the same thing. Or you want to say, where there was AEQ, we want to take in Q and DQ. I think that's it. I think we just need to know our position and speed. We want to do that for the BEQ function as well, all right? BEQ function as well, BEQ, right? And we run that should create those functions, assuming we did it right. Okay, didn't give any errors, moving right along. Nifty cool neato. So if I then now adjust my controller, so now its job is to run the optimization, grabs the torques, so it grabs the torques that it needs and then runs them on the robot, then we're done. Or at least we've got a functioning operational space controller, even though it doesn't do a whole lot yet. Okay, I'll stick around a little later. By the way, you all can leave at 10:45. All right, but if I had to stick another 5 minutes or so just to make sure that I get this working for fun with you all, I will. I absolutely will. So all right, so we're gonna do a couple of things. We're going to create some new functions here. We're gonna say we're going to simulate our functions. We're going to have our optimization inline function. Okay. And what we're going to run, so we're going to create a new function. We'll call it opt OSC for operational space control. What is it? What does it take in, my friends? It needs to take in the current state X. And I'm going to move, actually, I'm going to move this after all this other stuff. Excuse me. I'm going to copy it after these other dynamics functions here. Put it in between our taus here. Copy and paste it and just move it there. All right. So what's it going to do? All right. We need it to send back the first two elements of our decision vector. Okay. Well, let's do this one step at a time. Okay. Say quad. So we're going to run quad prog, okay? And quad prog is going to require the H function, the F function, the A function, which is open close. We'll just put open close so we know it's open close. The B function. Now we have our AEQ. We'll have to turn these into our functions. Right now I'm just writing the AEQ, BEQ. All right? Then I have the lower bound and upper bound. And then I'm done, right? This will return, this will take in some X and it should return the result of this quadratic program, which are the optimized decision variables. Okay. I'm going to start, this will make this a little longer. I'm going to do a little ... Okay. We're going to take quad prog. Okay. I'm going to break this out in line. So it's H func and it takes in our Qs and our DQs. And the way that we could compute our Qs and DQs, remember we create these functions called Q func X, which grabs our Qs, and our DQ func X here, which grabs our DQs, right? And sure enough, just do a new line here. Right. I believe I have, oh, sorry, I'm missing, I think, there we go. Fantastic. So this here is H func of Q and DQ, right? That's going to take in whatever our current state is, grabs the positions and says, here's our positions, here's our velocities, our Qs and DQs, right? And we're going to do the same thing and now give us our Hessian. Let's do the same thing, except it's got to give us our linear terms that we get from our gradient, which we called C-func, right? But same idea, C-func, right? Then we have open, close, open, close, open, close, new line. Then I have AEQ func. It's the same thing up here, right? Same thing, but it's just AEQ, right? AEQ. Then next thing, what is it? It's the equality constraints, the linear terms. It's the BEQ, all right? And then we need the lower bounds and the upper bounds. And we're done, right? Now, I'm just going to run this to make sure I don't get any errors. It has not changed the functioning of the simulation at all. We're still using that inverse dynamics controller, okay? But this should, but whenever we would call opt OSC was sending in the current state X, right? It should make this computation, right? So voila. Yes. Here's what we're going to do. Okay, so we're close. The only thing is it gives us, well, the result of this optimization, if we were to run it, actually, let's run opt OSC. Imagine we had a vector which was 0, 0, 0, 0. Does it run? Does it run, my friends? Sure enough, it does. Solver stalled. Constraint satisfied. Because the current step size is less than. Okay. Maybe that's just the right answer. That could be it. Let's try 1 second here. So, good. It works. Fantastic. All right. We did it. It solves quadratic programs. Now we just have to do it in the control loop. Okay. We'll see if that works. So this does the optimization for the OSC. But what we need to do is we need to grab the first two elements, because those are, my friends, those are the first two torques. That's what we want to send as our controller. So we want to create something called the controller OSC, right? We want to grab the first two elements of it. We would, and when we take in is equal to a function where we send in X, right? We can say, what do we want the two elements? We would say we have a 4 by 1. If we multiply it by a 2 by 4 with 1, 0, 0, 0, a little matrix math, 0, 1, 0, 0, and we multiply it by the result of opt OSC X. This first row will grab the first element. The second row will grab the second element, and that'll give me a 2 by 1 on the output, my two torques. Oh, look how smart I feel. Okay, just a little bit of linear algebra wizardry, okay? And if that's the case, that's controller OSC. If we instead, instead of saying our tau func is this function, I'm going to take that and say instead our tau function is just running controller OSC with X. This should run my dynamics by running a whole bunch of quadratic programs. Oh my gosh, this might work. Indeed it did. Oh my goodness. Oh my goodness, friends. Oh my goodness, oh my goodness, oh my goodness. Oh my goodness. That worked. That worked. It ran a bunch of, look, it ran all these optimizations, but look, it actually worked. It didn't do anything, which meant it worked. We were commanding a desired acceleration in the task space that was 0. If that's true, and if I instead command a downward acceleration in the task space, it should go straight down the end of that arm. Let's do that real quick. And again, you're all released if you want to be, but I am still streaming. I'm still going because look, this is the payoff, my friends. This is the payoff. Okay, so where do we define DDZ desired? DDZ desired. There it is. Right now it's 0. Let's define it as being 0 in the X direction, but minus 0.1 in the Y direction. If I do this right, it should command the robot to go straight down for a little bit. Okay? It might freak out at some point, but we'll see. Running it all. Look at it. Look at it go. It's moving. It's moving. It's moving that thing straight down. Did you see that? It did. It did. Let's make it move slightly faster because we don't want to go too far. I'm running it again. I changed DDZ desired. So now it's just moving straight down. Look. It even bends the elbow and it looks straight down. You see that? Incredible. It's not moving in some weird direction. It's moving straight down. Okay? Let's maybe move directly to the left. Make it so minus 0.15. This is the acceleration in the x direction to the left, right? Look how smart we are. Look at this. The end effector motion, right? Now let's make it go to a position, okay? Let's actually make it go to a position. The way we can do this is by saying we can have some KP, and we can use our, we're there, guys. We're there, friends. We're there, friends. Okay, here's what we're going to do. We're just going to write this PD control law, and we're good. Here's our PD control law, okay? KP plus KD. So let's write a KP. I'm just going to say it's 10. I'm going to say KD, our derivative gain, our proportional derivative gain are 10 and 3. Okay, so our DDZ desired, what we're going to do is we're going to have a Z desired. We're going to define where do we want this to go in space. Let's say we want it to go, I don't know, minus, let's make it, try to go at 0, 1. So that's going to be straight up in the air. That's where we want to go, okay? And DZ desired, the speed we want to have it go at, let's just say that is 0, 0. We want it to come to rest, right? So our DDZ desired is going to be equal to KP times Z underscore. So where do we want to go? So this is our desired minus our actual. So Z desired minus our actual, which is Z underscore, plus KD times DZ desired, a desired velocity, minus our actual velocity, which is DZ underscore. Okay, this is our PD task space controller. And we run it. Now it's in our cost. Everything should hopefully be all worked. We did it. Look, where'd it go? Straight. It's 0 units to the left. It's 0 units here. 1 unit up. We did it. Look where it is. Let's watch that one more time. We got to watch it one more time. I'm just going to grab the animation code. You can run the whole code all over again if you want. This is just the animation code. Watch it. Beautiful. You'll notice it overshot a little bit. That's just because we arbitrarily chose these gains here. Oh my goodness. We did it. We did it. And it will still work even if we add weight to it. It's just like, where's our gains? Where's our gains? Gains. So if there's overshoot, and you learn in controls 1 that this overshoot, if you have a derivative gain, that's like a damper that slows things down. So let me make that bigger, make that 5. Okay? All right? So, and that should hopefully run in a different way. It goes straight to the position that we want. Boom. Let's change the position we want to go to. We decide where it goes. Look, Z desired. Change the position. Let's make it minus 1, 1.5. Hopefully it can get there. Hopefully it's not too far away. If it physically can't reach that far, we'll see what happens. But anyway, everyone's released. Look at that. Look, it's going. And you could even change it so that way you have that position changing over time. Okay, you have to add a little time dependence in there, but you totally can. How neat is that? How neat is that? Did no one get this? Did anyone get this? Gosh, it's so neat. I'm just going to, you know what? I'm going to go to 0.1, 0.1. I'm going to have it try to bend in on itself. See what happens. What are you going to do, my friend? You bend in on yourself. And again, right, we're doing this code works fine, is running every single bit of the code over and over again. Every single time we run the code, it's rederiving the Lagrange mechanics. It's rederiving the task space and all its derivatives. It's rederiving the optimization. It's then simulating the problem. We're running the optimization inside of the loop, but it's running optimizations every single time step of the simulation. It is running this control loop. My friends, how awesome is that? And we did it. Okay, and this expands beyond just this simple 2-link robot that we have, right? If you can have more complicated dynamics where you have more generalized coordinates, And that's okay. You can add it so you have more, so you can have, you know, more motors and actuators. That's okay. This could be in 3 dimensions, and that's okay. The equations get tougher to derive, although there are ways of doing that. Come and take my advanced dynamics course in the fall if you want to learn some of those, okay? So, but from scratch, we do this operational space controller. And what does this do? What does this do, my friends? Well, let me see if, again, I'll pull up the video. I'll pull up the video that this is my student's controller, my student Tianza Wang, who is now, let's see here. Can you see this? Yes, you can see. Here we go. There you go. This walking robot right here is using operational space control. What is happening? He is designing, Tianza on the right there, is designing the task space targets. He says, I want the center of mass to move to this position and that position. And he's a PD controller that's driving it back and forth. And yes, the stepping makes it harder. The stepping around makes it harder. There's a model predictive control element of this as well, but that's higher level. But every thousandth of a second, it is running a quadratic program, and he's saying, I want my body to be here and rotate it in this direction. I want my feet to be in this position. Move my feet there. That's what it's doing. Those are its task space targets, the center of mass of the body and the feet. We just did it. That's the same math. Okay? What has changed from what we did to what Tianza did? Tianza had to make the code run even faster. So he ran, he was running solvers called OSQP. And look, it responds to disturbances like that, right? Okay? That's what's happening. Okay? Anyway, so interesting stuff. I think it's interesting. And but again, it's all the same structure. What else is different? I mean, the dynamics are much more complicated. We have a lot more degrees of freedom. I mean, how many degrees of freedom? I mean, the arm I just showed you just now. I mean, that's 2. That's 2 for that arm. You know, here you have 20 motors, so there's 20 actuated degrees of freedom. Then the base itself has forward, backward, left, right, and all 3 rotations, yaw, pitch, and roll. So that's 26 degrees of freedom. But in addition to that, there are also 2 springs that's spring around on each leg. So that's 30. That's 30 degrees of freedom. So the cube, theoretically, the size of the Q vector is 30, right? But it's still a quadratic program. It's still convex quadratic program, so it still runs fast enough you can run it on this robot. Yeah, so cool. Anyway, you can check out Tianza's published work. He now works for a humanoid robotics company, because of course he does. But this is how you do operational space control for something as complicated as a humanoid, right? So hopefully that was interesting. Hopefully y'all learned something and showed that, look, this is doable. Like this, let's look back at this code. You know, from start to finish, with some comments, how many lines of code is this entire controller and simulation? We don't need those extra lines. 231 lines with some white space. Anyway, so we'll have lecture on Tuesday in person. Okay. And we're going to do a project workshop on Thursday to help you with the projects. But in any case, good luck with your project update due Monday. See you all soon. Take care. Hope you had a fun time. I enjoyed it.